So when we have a model with only one or two predictors, we've seen how to test specific hypotheses about those predictors, right? Typically that involves comparing differences across groups. But what happens when we have more complex models, say the three predictors, and we start adding interactions, etc.? Or what if we want to test some very, very specific hypothesis only about two groups, for example, or two groups conditioned on something else in the other predictors? So when we have complex models and complex hypotheses, well, it's a lot more complicated to do that. And specifically, it's very complicated to properly interpret what the coefficients mean because of the additive nature of the linear model, the dummy variables, interactions, etc. So it's kind of next to impossible to properly compare these group means while controlling for the other factors of interest. And as a consequence, well, very often we kind of have to fall back to just looking at the raw mean scores or running very simple tests that ignore the other factors. So we lose the power of the linear model because at some point it turns into something very complicated to work with. But well, we're going to see now what are simple ways of using still all the power of the linear model to test these hypotheses in these scenarios in which we want to control for multiple things. So let's start with a simple model. Say, in this case, again, we're working with the wage of employees by different factors. And in this case, we're modeling wage only as a factor of education, anywhere between primary school, high school, bachelor, master's, or PhD. I could ask the question, what's an estimate for the insured employee with a master's level education in IT and 30 years old? That's a very specific question, right? I could also think about possible comparisons. So let's compare a person with that profile, but instead of IT, let's say industrial. So everything else being equal, what happens if we go for industrial job class? So let's say the model in this case, it's something like this over here. We have each of the dummy variables, and they correspond to a deviation from the reference, which is primary education. So we see that, yeah, it looks like for the primary education, we get 84, I believe this is $1,000. But this doesn't account anyway for the age or the job class. It's only education. So here's both industrial and IT. It doesn't care for insured, etc., etc. So here we are not really able to test anything about these two research questions with this simple model, right? Anyway, what we say is that the higher the education, then the higher the deviation from the primary. Makes sense, right? Everything is statistically significant. Okay, that's good, but doesn't allow us to answer the research question. So when we have a little bit more complicated model, in this case, we have also the class, the job class and education, plus the interaction. Then we have a model like this. All these terms are about the education. This one is about job class, and all these are about their interaction. So if we ask the first question, what are the terms of the model that are involved into answering that question and provided that estimate? Well, we have, of course, the intercept. Then we have a deviation for master's studies. Then we have a deviation for IT and a deviation for the specific combination master and IT. So we would need to add 83 plus 8 plus 5 plus 1. But now we lost any measurement of uncertainty into that estimate. And that measurement of uncertainty is calculated from the standard errors that are not here and the correlations between the coefficients, which are typically not even reported in a regression table. What happens if we want to go for the second question, that profile, but in an industrial job setting? Then we need to drop this coefficient and that coefficient. So it's only 83 plus 8. So we are able to get a probably better answer, but still it's not good enough. So we go for an even more complex model. And in this case, we are considering education, job class, age, insurance, and all the two-factor interactions. So what are the coefficients that are involved into this estimation for that profile we're looking for? Well, of course, we have the intercept over here. Then we have a deviation for master education. We have a deviation for IT. We have to consider the age of 30. Then we need to consider interaction between master and IT. Here it is. Then we need to account for the interaction between age and master. Then we need to account for the interaction between IT and age. And I think I'm done now. See, I'm not even sure myself whether this is complete or not. I think so. So now we add all these estimates and we get the answer. What if we want to say again the same profile but for industrial setting? Then we need to drop this one interaction because it's only for IT. Then we need to drop as well this one, master and IT, and then we need to drop this one as well. We sum the estimates and then we got our final answer. But how can we statistically compare the two groups, job class IT and job class industrial, for this one specific profile? And how can we quantify that uncertainty? We're still wondering how to do all this. So let's enter ANOVA again. So we have a complex model like the one before. This is the corresponding ANOVA table. So now we have all the main effects over here, all the two-factor interactions. And we see that, for example, it looks like there's very clear interactions like this one and that one probably, and all the main effects. But still, if we start looking into an ANOVA table to answer research questions about specific hypotheses, again, it's not very useful because I could look into this one here. Yeah, that's a very significant result. It's about the interaction between education and class. So that means the differences between education or differences between classes are not constant across the other factor. So the differences between industrial and IT are not constant across education levels, for example. Well, sure, that's something very useful to know, but still it's not giving me the option to test specific hypotheses. I know there are differences in there, in those combinations of education and class, but where are those differences? And what if I want to test specific combinations? And the same thing happens here with the main factors. Yes, there's very clear differences between education levels, but where exactly and what kind of differences are there? Can I test specific education levels? So yeah, ANOVA still tests very specific hypotheses. It's not that very useful. So what can we do? Well, we enter the world of estimated marginal means, or EMMs. So in these situations, we can do estimated marginal means. They're also known by adjusted means. And the thing is that they're going to allow us to estimate the mean response of the model for a certain group or combination of the factors in general, while controlling for the effect of the other factors in the model. This is the important part. So we're going to be able to provide estimates for whatever combination of the factors we are interested in, while controlling for the effect of the other factors. And of course, it can also be used to estimate the mean of a numerical variable. That's fine. But normally we're interested in categorical variables, in comparisons across groups. How does it work? Well, the idea is that we're going to give the same weight to all the possible treatments. So to all the possible combinations of the factors, we're going to give them the same importance. It's kind of enforcing the balance in the data set. So every possible combination of the factors is going to have the same importance into the estimates. And by the way, it could be misleading to estimate the response in a certain population. So if it so happens that in the population that we are studying, where we gather the data from, there's a lot more industrial jobs than IT, well, then so be it. We should consider that when making our claims about the data, right? But if what we want to study is not this specific population, but understand the underlying properties of the factors and how they interact with each other to affect the response, then this makes more sense, because we're actually going to try and understand the idiosyncrasy of the process generating the data. And of course, it comes with the full machinery of standard errors, intervals, p-values, etc., etc., etc. So everything is based on the idea of a reference grid. And it's nothing but there's this big table in which we have one row per combination of the factors. In our case, it was the age, class, insurance, and education. By the way, for numerical variables, we typically just use the mean, but we could use something else, even more than one value, if we have, for example, nonlinearities. But in the typical case, we just have the average age. But then for class, we have both industrial and IT. For insurance, we have yes and no. And for education, we have each of the possible education levels. Then what we do is, or what the software is going to do for us, is to compute the estimate and the standard error of that estimate for each of these combinations of the factors. So for any possible combination of the factors, which would be the response of the model and the standard error. And so if we want to look into the estimate for a specific group, what we do is average in this table all the treatments that would correspond to that group. For example, if we want to get an estimate for a master's level of education, what we do is average this 101 and this 105 and this 127 and this 132. The answer would be 116. And by doing this, we see clearly that we are assigning the same importance to all these four combinations. We're giving the same importance to industrial no insurance master, to IT no insurance master, to industrial yes master, and to IT yes master. We are enforcing this balance into saying all these are equally important, all these have the same weight here in the computation. And we can go beyond just the one factor. We could say, what's the average weight of the estimate weight for a master education in IT? Then it would be getting this one, 105 with 132 over here. The answer is 118.5. So for any combination that we want to study, it's about averaging all the rows in this reference grid that pertain to that one group we want to get an estimate for. And again, it's going to come with the full machinery of standard errors, p-values, intervals, etc., etc. Let me show you an example. So in general, these expected marginal means from the model will be different from the observed means, from the raw scores we get in our data, because it's based on a model, and because it's based on a model, it's going to start controlling for interactions, imbalances in the data, and etc. So for example, here on the left, we have the observed scores for an average wage in industrial or IT, or no insurance or yes insurance, or each of the education levels. Here on the right, we have the estimated marginal means in the complex model we saw earlier, in which we have all these main factors and interactions. And so we see very clear differences. For example, the first one is that small wages become larger. So it's not 103 only, it's 106. And it's not 92 only when you don't have an insurance, it's 99. And of course, the large wages become smaller. So it's not 121 as we observe here for an IT job, it's actually 110. That's a big difference. And it's not 120 when you have insurance, it's actually 118. Those are differences that arise because of the model controlling for different factors and imbalances in the data. We will see later why we have these differences. And there are also smaller gaps between groups. For example, between industrial and IT, now the difference is smaller because, of course, the small are getting larger, the large are getting smaller, so difference is not that big. Here we have a difference of only 4 units, 4K, and here we had a difference of 16. And the same happens between, primary education and PhD. It's not really that big. It's actually something smaller. There's reasons why the model is telling this. What else can we do? Well, we could facet. So, for example, we could look into differences across education levels by job class. So in this case, we are again looking into the observed scores over here and the estimated marginal means over here. What difference do we see? Well, the high wages seem to be overrepresented in PhD jobs. So what this means is that the difference between the observed PhD industrial here and the estimated PhD level here is very large. And especially, for example, master and IT, the difference between 127 and 119. That's a very big difference. The others are not so different. So primary industrial 83 or 84, 95 for high school, 95, 106, 106. Those are still being estimated kind of the same as we observe in the raw numbers. But there is a big difference between master and PhDs. So there's something going on with master and PhD education levels in the data, because once we start controlling for something else, we see that their estimates are smaller. And we can have confidence intervals. So here, for example, 95% confidence intervals for each of the estimates. Those also provide us a sense of variability in the estimates. So it's not just about this 84 here, it's about the variability of that 84. This is something that now the estimated marginal means allow us to compute for, in this case, different education levels faceted by by job class. Let's see another example of faceting. So here we're looking into differences between having insurance or not, and we're again going to facet by the job class, industrial or IT. So what we see is that the low wages seem to be overrepresented in industrial no insurance jobs. So industrial no insurance jobs, this case, this 88, might be overrepresented in the data, because once we start controlling for other factors and controlling for the imbalance, that 88 turns into 96. That's a very big difference. And similarly, the high wages seem to be overrepresented in IT with insurance jobs. So this 127, once we start controlling for other things, turns into only 120. Well, only 120. And what that means is that there's probably an overrepresentation of high salaries here and an overrepresentation of low salaries in this case. If we start controlling for that, then this is what the model is telling us. Again, with confidence intervals, etc., etc. So it's already hinting into possible overrepresentations of specific cases in specific combinations. And of course, we can also do comparisons or contrasts, group comparisons between, in this case, for instance, job class, industrial or IT, by education level. So if we just look into the observed scores, then we see between industrial and IT, there's a difference of 5K or 3K or 3K or 3K, 20K, depending on the education level. But now with the estimated marginal means, which are again based on a model controlling for other things beyond this only industrial IT education, we are also controlling for insurance, we're controlling for age, we're controlling for interactions. Then we see a quite different picture. From the observed scores, it looked like in all education levels, the IT jobs have a higher salary because this is always negative. But if we start looking into the model, then the picture changes. For primary education, yeah, it's -3, but look into the confidence interval and p-value. The conclusion now would be we don't have enough data to support the hypothesis that there's a difference between industrial and IT jobs with primary education. Look into high school. Again, not enough evidence. Look into bachelor. Not enough evidence. Look into masters. Not enough evidence. The only case in which we do have enough evidence to say there's a difference between industrial and IT is PhD level. That's the only one. And that's something that now we can do here thanks to the model and the estimated marginal means. We can look into specific differences. We can have p-values and confidence intervals, which is something we did not have over here. So it's not only that we are controlling for other factors when making these comparisons, it's that we have all the statistics about those comparisons. And now we're able to make more informed decisions based on better conclusions from the model. And so let me give you another example of contrasts. In this case, we have the contrast or the comparison between insurance yes or no by job class. And what we saw is that in general, in industrial, if you have insurance, you should expect 24K more than if you don't have insurance. And in IT, it should be 28 more. Okay, that's fine. But if we start looking into the model, those estimates turn into 19 and 20. So you see, the difference is actually smaller than it seems. And here we have confidence intervals, p-values. Yes, they're different from 0. We have a quite wide confidence interval, if you ask me. But what this is telling us is that the gap between having insurance or not is actually smaller. And it's actually more similar across job classes, because it looked like the difference here is larger in IT than in industrial, but it turns out to be basically the same. If you look at the confidence intervals, they're basically the same. So there's no difference between industrial and IT when comparing insurance, yes or no. Why all these differences between the observed scores, the raw scores, and the model? Well, basically because of two things. On the one hand, the model accounts for other factors and their interactions. So here, for instance, in this plot on the left side, we are plotting the relationship between the wage and the age. We are faceting by insurance, yes or no. We are faceting by job, class, industrial, and IT, and we're plotting separately the education level. And what we see is that the lines are, of course, not parallel to each other in all cases. We have different intercepts. We have many different interactions. So because we now build a model around all this data, taking into account all these different factors and interactions, we have a better answer to the research questions. When we only look into one contrast, like insurance yes or no, we're typically going to conflate all the job classes. And we're probably going to conflate all the different education levels. So we're looking into only a line that looks like that in this case, and probably something like that in this case. And we're even ignoring these lines altogether because we're ignoring the factor age. So by including all this information into the model, we are drawing better conclusions. And the second reason is, well, the EMMs account for data imbalance. What's the problem here? Well, the thing was that primary education or jobs that require primary education are overrepresented in the industrial setting. So if we compare here how many primary education jobs, there are many more than in IT. And we know that primary education jobs have a lower wage. Therefore, it might look like in industrial jobs, the wages are lower. But it's not the wages are actually lower. It's that there's more overrepresentation of the low-paid jobs. That was the reason why we saw the difference. And there's a much bigger representation of high school education than in the others. And of course, in PhD with insurance and IT, we see a lot more cases than in the others. Those are very highly educated people with very good jobs, probably. They're paid a lot. That's why they are overrepresented in IT, and that's why they're skewing the wage of IT, or apparently skewing the wage of IT towards a high value. So all these imbalances in the data are something to take into account when comparing across groups, etc., making predictions, because if we only look into the raw data without building a model around it, we are going to fall for all these traps. We need to build a model to account for all this. And so let's go back to the two initial questions we had. We're interested in this specific profile, insured people, master's education in IT, 30 years old, and then the difference with industrial, everything else being equal. And the model we had accounted for all these factors and all the two-factor interactions. Let's compare. So if we just look into the data, into the observations, we could actually say, okay, give me all observations of 30 years old, insurance, yes, master education, and then industrial and IT. Well, it turns out that in the data set, we have 4 observations of industrial and 9 observations of IT. If we were to compute the average wage, the difference will be here, 116 versus 128. So this would be the answer to the first question, and the difference would be the answer to the second question. So that would be a plus $12,000. Once we have the model, we can actually provide a better answer by controlling for these other factors and looking into the estimated marginal means. And so what we have here is these two estimates. And if you notice, the estimate for IT is basically the same, 128, but the estimate for industrial is higher. The difference is only 6. So here the difference would be plus 6 in the second research question, that one there. And of course, we have confidence intervals over here. Now, if we want to make the actual comparison, because yes, we have one estimate for industrial, we have an estimate for IT, but we want to compare one against the other. We want a confidence interval, for example, for their difference. We want a p-value. How do we do that? Well, if we look into the estimates again, no model, the difference would be the negative 12 that we saw over here, right? But now, thanks to this estimated marginal means, we can look into the contrast. In this setting, 30 years old insurance master, we can look into the contrast industrial versus IT. And the difference would be this 6 that we saw over here, but now we have a confidence interval for their difference, and we have a p-value. So by normal standards, we would say it looks like there is a difference in this specific profile between industrial and IT, but we might need more evidence to support that with more confidence, because so far, the p-value is considered to be high or high enough to not really make that claim. So again, this shows the powerful addition of the estimated marginal means on top of a model to really study any research question we want through the model, any specific combination of the factors and contrasts between the factors.